Hey everybody, we're going to do vectors today, and this little arrow is all important in vectors because it's key to the whole idea of vectors. So first thing I'm going to do, I'm going to ask you a question. The question is this: what's the difference between speed and velocity? As Gordon Strachan was once asked for a quick word by a journalist. He just turned around and said velocity. He could have said speed, but what's the difference? Well, I'll tell you the difference is speed is a straight measurement of size, so about how fast you're going. Velocity is that plus it has a direction. So velocity is speed combined with direction. Now, what does that mean? So vectors. Before I do vectors, I'm going to talk about scalars first. Okay, so scalars are the other thing. So a scalar quantity is simply anything in life that can be described by just a number. So a bit like speed, it's just about size of something rather than doing it. So that's a scalar quantity, and scalar just measures size of something, like the temperature or my age or something. However, a vector is a quantity that needs a direction as well for it to make sense. So vectors have both magnitude or size and direction. Let's give an example. So velocity has speed and direction, so it could be a wind velocity is 20 kilometers per hour in a due east direction. Speed of the wind is just 20 kilometers per hour, but the velocity is 20 kilometers per hour in an east direction, and they're called directed quantities because the size that they have is directed in a certain direction, for want of a better word. Okay, so what do they look like? Vectors can be expressed as straight lines, so like this. And as you can see in the straight line, it has an arrow, and the arrow indicates the direction. It has size, it has a size of the line, but it also has a direction. They can also be listed as column vectors, and we seen these when we did translations earlier on the year, and they look like that. So the 3 indicated 3 to the right, a minus 3 would have indicated 3 to the left, a 1 indicates 1 up, and a minus 1 would have indicated a 1 down. So there are ways of expressing them, and the column vector would look something like this. So 3 to the right and 1 up, so your vector would actually look like that line there. So travelling from that point in the left to the top right, and that would be what that column vector of 3, 1 looks like. And it's sometimes said that vectors are pathways, so they show paths from one point to another. Okay. The most common notation for vectors is actually 3 different types. You might see that line represented AB, so line going from A to B, you can see the direction is AB with a line over the top. They might call it the same letter as the origin letter, but in bold, so a big bolded lowercase a, or even an A with a line underneath. And then, as we go through some of the past papers, you'll see all 3 types come up, and at a certain point you'll get more familiar with them, especially the first one. You're probably thinking makes more sense than the other 2, but usually the other 2 are actually marked on the diagram to help you out, and you'll actually see this coming up in some of the examples. So resultants are the single vector, which is equivalent to a single vector. Probably, what are you talking about? What the hell are you talking about? So consider we have this vector A going in that direction, and this vector B in that direction. So the result of adding A and B together, like so, would be a new vector, a single vector. So we could, this is why pathing, it's sometimes called pathing. Okay, I could go from that point to that point, or I could go up to there and down there. Now certainly one path's longer than another one, but that path is equal to, I could either go that path or I could go that path. So what we say is that this vector here is A plus B. Now bear in mind the direction. I'm going in the direction of A and I'm going in the direction of B, and that's the pathing. So if we call this the last vector C along the bottom, we could say that C is equal to A plus B. What if this one was called A and this one's minus B in this direction? Well, again, C would be A minus B. Follow the path and follow the direction. Let's look at some of the properties. So vectors with the equal magnitude and direction are equal. So even though they mightn't appear in the same place in the diagram, if they're exactly the same size and the same direction, then they're equal. So if vectors have the same magnitude but opposite directions, then we just reverse the sign of the vector. So AB, if AB was A, if we went from B to A, that would be minus A. So you're nearly like travelling against the grain. It's a bit like when my dad was teaching me how to saw wood and stuff. You know, you saw with the grain to make it easier. If you saw against the grain, it's harder. So if you're like going against the grain, it's a negative vector, and it's fully negative the other way. If different size vectors have the same direction, they are scalable multiples of each other. Scalar multiples of each other. What does this mean? So we have two vectors there. They're going exactly the same direction, but they're different size. So basically one is a multiple of the other one. In this case, we're going to use the letter K to denote what the multiple is. But if we've M and N, then M is so many times N. That might be twice, it might be 1.8, it might be a smaller value than that, but who knows. In this case, M is twice the length of N. And we can say that because they're going exactly the same direction, so the directions are the same. One is just twice the size of the other one. Resultant vectors can be broken down into component vectors. So A is that, and it's x, y, and x is that, and y is that. So, sorry. A is so many across and so many up. So when we're writing our translation vector before, we're going so many to the right and so many up, or we're going right by x and up by y. And that's the way we would write that. It's kind of repeating what we did before, actually. Vectors can be written in terms of other vectors. So we have an A, and we have a B, and we have a C. We could see, just like we did before from resultant, that A plus B equals C. Because we can we can take that path, or we can go that path, and that will take us to the same starting point and end point, so they're the same. Okay, so we're going to rewrite the following vectors in terms of A, B, and C, and we'll have a lovely label diagram here of A representing A to B, B underlined being B to C, and similarly C should be underlined, but bolded C is from C to D. Okay, so if we want to describe BA in vector terms, well, it's this bit here. We are going against the direction of that vector, so it is going back that way, and it's minus A. Similarly, CB is going against the vector B, so it's going that direction, and it's minus B. Similarly, DC is going back that direction against the C vector, so it's minus C. If I want to go from A to C, well, the pattern I could do is go from there. But the vectors that we've been given, and the questions usually will be using vectors already getting, how else can I get there? Well, I can go A plus B in that direction. And similarly, D would be, instead of going the direct direction there, we're going A plus B plus C gives me that. Okay, let's take the training wheels off a little bit, and let's try this one. Alright. First one we're being asked for is E to D. Now E to D doesn't seem to be here. However, I said earlier on that vectors of the same size and direction are equal. So I can look elsewhere in my diagram and see that E to D is the same as A to B. So it's the same direction, same size. So E to D is equal to this vector A. What about FE? Well, FE is going in this direction, and it's the same as B to C. So it's going to equal the vector B. A to F, similarly, is parallel and the same as C to D, so it's going to be this vector C. What about A to E? Well, A to F is C, and F to E is B, so that one's just going to be C plus B. DA is, careful, now DDA we probably would take, we can go either way, right? But we can go that way, that way, that way. Okay, so if we travel that way, it's against that vector, so it's minus C and minus B And that should be minus a at the end. Dear, dear, dear. What are we ever going to do there? That's terrible. Let's change it so that future generations never get stuck again. So C minus B minus A. What about BDF? This should help you out. So we're going to go back along this way. So it's going to be minus A. And that one was plus C. So it's minus A plus C. E to C. It's going to be plus A minus C. Yeah. And DF is going to be from there to there. So I'm going to be minus A minus B. Last but not least, rewrite the following vectors in terms of A and B. Now, we've got to do AP. Okay, so we know that A is this length here. And A, if I tell you A, B, and N are the midpoints of each of those lines. Right. AP is the same length and the same size as that one there, so it's just equal to A. Similarly, A to B, I can go that way. So the path I can take is back here. So I can go minus A plus B, or B minus A if I want to turn them around. OQ. OQ is there. Well, we know this is B, vectors B, and this one's identical to it, so it's twice the size of it. So it's going to be 2B, or not to be, that is the question. PO. PO. Right, we know the length of this is A, the vector of that is A, we know that the vector of that is A, so that whole thing there would be 2 plus 2A, but we're going against the grain, so it's going to be minus 2A. PQ is this one here. So to go from there to there doesn't seem like it should be that easy, but we could travel that way by going from PO and then OQ. So if I add these two together, I'm going to get minus 2A plus 2B, or 2B minus 2A, depending on which way you're doing it. PN. Well, if I know that this one here is 2B minus 2A, well, this is half of that. So I'd half each of these values, and I would get B minus A. ON is 2A plus B minus A. So the 2A minus the A gives me 1A plus B. AN is there to there, so it's A plus PN. So it's A plus B minus A. So it's just going to be the mu with B. BP, I can go B, and then I'm going QP. So it's the opposite of this. So it'll be plus 2A minus 2B. So of B plus 2A minus 2B, so it's going to give me 2A minus B. And last but not least, QA is going to be from there to there. A couple of ways to do it. I can go minus 2B plus A. Okay, and questions are generally of that form. They might get you to add and subtract the vectors like we did in translations, and we'll cover that, or they might get you to show the path and describe the path from a diagram just in vectors. And that's really the topic. I'll bring in some past paper questions on Tuesday, let you have a look at them, see what you think. As one of the students is already, they're a bit head pickly, was the phrase that they used, which I will certainly agree with, because you've got to spot the path to get from one to the other, trace it with your pen, and then work out if you're going against the direction of the vector or with it. And that's how we go. Okay. So let's look at a harder question. Let's look at this one. So we know that AB is the vector R, and we know that AD is the vector S. We know that AY to YD is in the ratio 1 to 2, and DX to XB is in the ratio 1 to 2 as well. Now we're asked to show that YX is parallel to AC, and what is the ratio of Y to X to AC? The ratio bit confuses people, because essentially what's been happening, if you think of ratio, in a ratio 1 to 2, you're splitting something into 3 parts there. 1 part is there and 2 parts there, so that's 3 altogether. So AY is going to equal to a third of AD, and YD is going to equal to 2/3 of AD, and similarly for the D and B. Okay, so first thing to do is we are going to set up our solution. We're going to label our diagram. We're going to put our S vector in there with our arrow, and our R vector up there with our arrow. And we're going to point out that the vector AC I can do by doing plus S plus R, because the AB is parallel and this and the same size as DC. So AC is like that. We also are going to need the fact that DB, need this one here. To do that, we could go minus S plus R or R minus S. Now, if we want to work out YX, we can use this bit here. So this is bit from YD is 2/3 of the line, or 2/3 of the vector S. So that's 2/3 S. And then we know that this bit here is 1/3 of dB. And if we know dB is R minus S, then it's 2/3 S plus 1/3 of this R minus S. If I multiply out that bracket, I get YX equals 1/3 of R plus S. How does this help us? Well, first thing, it shows that they're parallel because they both contain the R plus S. That says it's the same direction. R plus S, R plus S. So that shows that they're parallel and you can tick it. Then it asks what's the ratio of YX to AC. Well, we know that YX is the third of this. So that means the ratio is 1:3. Because for every one of those, there's 3 of those in length. And that's the solution to your question. Hope that's some help to you. If not, you can bring the questions into class and I'll see you then. Okay, take care. Bye.